now know enough about wireless with the performance of its air interface and propagation and how to design systems that basically we've reached the sort of envelope that wired networks have already started to grapple with, like DSL and cable. And basically it says, if you give me the equation that relates power level to noise to bandwidth to rate, and if you give me a certain amount of power that I can transmit over my system, basically I've now reached the point where I can just about tell you what kind of service I can deliver. And there's not a hell of a lot of extra that you can go before you run into the Shannon blockade, which says, you know, this is pretty much a limit. I now have to find a new way to go to make the network better. So, you know, in our design of networks, kind of humorously, I've designed a chart that shows you kind of two things. The half-life of information, that is, how long it takes before information is kind of worth only half of what it was, and also how far you're willing to go for important information. And clearly in the physical communication era where we used to send letters and things, it took us quite a while to get information, and consequently the information lasted a long time usually too. As we got into the wired communication era, things started to shorten. And basically we began to go to like the house next door, which had a telephone, and the information lasted, you know, maybe half a day, if you were lucky, a few hours. But now we're getting to the wireless era where we all carry our communication with us. And what this has done is change not only how far we go for communication, but also how long it's valued. And that's kind of an interesting concept, because what it says is the number of people standing at the airport next to a payphone is virtually zero, because everyone's talking on their handset. So I submit that the metric now is the length of the arm is about as far as you're willing to go, and a couple of minutes probably is the half-life of the information. But you notice, somewhat humorously, we still have a ways to go. The telepathic part. Now you may say, well, that's a little silly, but it's really not, right? Because we've always changed the essence of human thought into something else, kind of a surrogate that carries the idea to another person or another place, right? And so telepathic is nothing more than converting the thought itself, maybe with brainwaves, to some other physical communications medium, like wireless or wired or, heaven knows, maybe smart cards or written stuff or RFID, right? So people are already playing with us. They're already installing brainwave readers in jet fighters so that you can pull up before you hit something just by using the thought of saying pull up, because you may be under too many G's to actually operate the stick. And in fact, there are games that actually allow you to tune your ability to do this sort of psychic connection. But what I submit is, all we've really done is shorten the distance getting to our thinking process down into sub-inch region. So I think this will go on for a while. So now we get into the meat of it. Let's level set a little. Larry and I know that what first generation cellular was analog, used big cells, incomplete coverage, non-uniform quality, and call drops. Remember all of those irritations that people dealt with. In responding to them, we then went to 2G systems. These are characterized by digital transmission, a mix of large and smaller cells, nearly ubiquitous coverage, meaning you can usually get service anywhere. Whether you really want to use it, that's another thing. But nevertheless, it had better quality, still not quite full quality, you know, QoS like wired systems, but it was backward compatible, so it enlarged the thinking. Then for 2.5G, we recognized that data was becoming bread and butter too. So we added data, cells got even smaller, even down to microcells. Much more ubiquitous coverage and capacity too, not just coverage. Lower blocking, slow packet data, and backward compatibility. Then 3G. This is where we may have taken a bit of a wrong turn, or at least we found that kind of rumble strip over near the edge of the road. And the reason is that 3G extended its thinking from the switch circuit world. But at the time 3G was maturing, from initial thought to real systems, something else very powerful was happening. The internet, data and multimedia happened. And so 3G, already in progress, had to not only take what it had to develop, but also, while the plane was flying, kind of try to change the engines without crashing. And that's what 3G is still doing, in my opinion. So basically, smaller cells, packet plus circuit operation, supportive slow multimedia, so that you can get more than just voice and bursty packet data, and backward compatibility. Now we come to a sort of fork in the road, as Johnny Carson used to say. Basically, we've now reached an appetite for bandwidth and multimedia, and by carrying our devices with us, the ability to produce dense clusters of people, so that the teledensity, the appetite for rate, and basically the character of systems is basically changing forever. It's kind of almost discontinuous. It's like we wanted 3G, but we wanted it like 8 years ago. So what are we going to do now? Right? And I submit that 4G is probably that answer. And like previous types of systems, 2G, 3G, and so forth, I think it's part of a growing mosaic of connectivity. It's not a replacement, it's a supplement, right? And I think it'll have a broadband digital PHY, so it will become the wireless equivalent of what people call singing and dancing broadband multimedia, like you get from the cable company or DSL. And I submit also that it will actually get us into cells that are so tiny that actually they can be called nanoscience, maybe 1,000 feet. That its coverage will be viral, which is, I guess the nice way of saying this is organic, which means that coverage will grow where the demand and willingness to use the system persists. So that basically it grows the way an organism grows. Now cellular followed a sort of coverage first design, and you'll see that later. And lastly, a wired, a computer network paradigm, Ethernet-like, a network of networks sort of view, right? But underlying all of this, higher capacity, better quality, like wired if we're courageous enough to step up to it, and more throughput per user. So the service environment is changing a lot, and that's part of what's changing our appetites for communication. It used to be we operated over wired and some wireless, and basically we had separate systems with separate appliances and separate services to do what we wanted to do over those systems. What I submit is we've crossed over with the millennium into a new environment called a merged service environment, where basically a variety of appliances, a variety of services, and a variety of uses will get together. And this is an important change, because combined with the excitement of multimedia, and by the way, I view that as a sort of step function in what might be called the wow factor, right? Which is, oh wow, I want it, right? This is like plasma TVs and HD TVs, right? It says, stuff that's cool, I will pay extra for. So I think the network of the future is speaking to you. It wants to carry this, right? And people want it. So that means that a wide variety of information services, which had been sort of smokestack or partitioned, like these, basically with the internet, have become a sort of giant cosmopolitan mall where you can share different kinds of information. And the devices have evolved to be not just a phone or a pager or a television, but now they're multi-purpose instruments. What you need is a network in between to make it all happen. And if you can, you violently change the marketplace and even the economics of literally society. And just as an example, on the left side you sort of see various information forms, and on the bottom information management sort of things, right? And right now, various industries kind of live compartmentalized in various segments of this chart. But that's now changing rapidly because of the internet, because of multimedia, because of relational databases. And consequently, these are now growing. So they spread out to more of the charts than they used to. And indeed, with that short distance you're willing to go for information, and the short half-life of information itself, 4G ought to have a big part in this. So, hopefully I've set up in your own mind the value that it can have. Here's the value that we already know it has. People love Wi-Fi. They really do. And some estimates have put ridiculously high numbers on Wi-Fi. Why is that? Well, at the gut level, it did something that people wanted. And they thought it was cool. The price was right. And because it was so flexible with its Ethernet philosophy and computer-like management paradigm, people could develop applications as easy as you do new things on the internet. So very powerful. And it became a worldwide phenomenon. In fact, various world governments have put aside radio spectrum, working together with the World Radio Congress to begin to make this what might be called the first worldwide communication wireless revolution. And now, you actually have the capability in many countries to get off your airplane in an airport and log on with your 802.11 card. Well, this is pretty cool. So, if we go forward and we think about what have we learned over the years? Clearly, radio and then cellular and then digital signal processing, all of that stuff, it made us smarter. We learned how to use radio better. One of the things that clearly came out of that was, if you can get the price and the performance right, the cells will probably get smaller. Why is that? Well, you use spectrum more efficiently. You can probably predict what will happen better. And more importantly, you can get the capacity up. So all of those things position the 2G sweet spot that was kind of in here. Now 3G seeks to carve out a space in this area, and things like WiMAX do as well. So these are the so-called metropolitan area networks, right? Cell sizes maybe 0.5 to 2 miles, that sort of thing. What I submit is that 4G will put us into this area, and that will make an important distinction. Now, why would you do this? Well, if you end up with cells that small, you'll probably end up in a neighborhood-like environment. So if you look at the behavior of radio signals in that environment, and you look at the equations, basically what you find out is height has a big factor in determining how soon you descend into multipath. And multipath is nature's way of telling you, I'm eating you. Basically, I'm eating your signal up or making it hard to use, and consequently you begin to see a disproportionate power budget in order to communicate information. Moreover, if you want to make it broadband, now you have to work even harder because you need really good signal-noise ratios. So the bottom line is, and we discovered this in cellular over the past 10 years, there's a thing called NIMBY. Anybody know what NIMBY is? Not in my backyard. That's what NIMBY is. And basically it says the tall towers that cellular systems like are something I want, but I don't want them in my backyard. So it says, if you're going to deal with small cells, you may have to deal with an environment that's very much like the one you live in every day, your street. What's the maximum height that you'll stand in your street? The answer is it's probably a lamppost height, or something like it. So if you look at the kind of models you get for that kind of height, it shows that you start to run out of propagation gas with battery-operated devices on the order of 1,000 feet or so. Moreover, you may need that in order to get good connections anyway. And the good news is that you can actually, with these smaller cells, supplement it by cell sites that you don't put in just where you can get rights, but rather you can position them so you can actually make a miniature micro-universe for radio signals. You can actually better optimize the coverage. So this allows you to do what I call neighborhood area networks. And this is a topic that I recently spoke on at the 802 plenary in Atlanta in March. And it got a lot of interest. So I hope you're interested too, and you might follow through with maybe work on neighborhood area networks. This gets to some of the learning. I won't go over this chart in detail, But this speaks to that kind of chart I showed you before. You know, the kind of technobond where the learning leads you to the Shannon zone. Well, basically, in the Shannon zone, I think we're sort of getting into this area now, right? And basically we're saying things like OFDM and even UWB, those sorts of systems are the way that we will get to Shannon. And the modern communication systems of the future, like 4G, are going to use this surgical application of spectrum to provide the kind of performance and coverage that will characterize 4G systems, right? Now, this is something that many 3G people would probably not like you to know. But the bottom line is, you know, Mother Nature doesn't give you anything for free. And handheld devices like this one use a battery. So if you want to send information over a distance, it's dependent on the bandwidth and the amount of power you have. And that will set pretty much how far you can go. So the issue here is that unlike radio and indeed electronic devices, batteries, in terms of energy density, whether you choose, you know, watt-hours per pound or watt-hours per square inch, basically it hasn't grown like Moore's law. And the reason is batteries are chemical systems. And if you say, you know, look under, let's say, a bomb in the dictionary, you know, say a chemical system that releases a lot of energy in a short period of time. And really there's little difference between a bomb and a battery. It's really just the rate at which you let the energy out. So battery manufacturers well know that if you make a battery, you'd better be prepared to make sure nobody gets hurt with one. And so, because this means that energy density grows slowly, you have to be careful and you have to rein in your expectations about how fast and how far you can go with a system that depends on the battery, right? And NEC learned a hard lesson, right? Because they created a new kind of hotspot with some of their phones, because the battery shorts out and literally begins to heat up itself, right? Now the other part of it is, if you look at macro and microcellular systems, and you transmit continuously, like a video call, at very high speed, well, the predictions are that you might have a relatively disappointing battery life, right? So again, 4G systems can come to the rescue, because that benefit of power efficiency over the distance at high bandwidth really pays dividends, right? So again, I think 4G becomes important. But a trick with 4G is, how do I keep it inexpensive? And I think here computer technology showed us the way. In the old days, cellular and IBM mainframes reigned supreme, and they used a relatively dumb terminal network with a relatively smart controller. But I think we all realize that PCs now are pretty smart all by themselves. And networking makes every one of them as powerful as any of them. So basically 802.11 can evolve to be that way too. So be it mesh, or be it an ad hoc network, or even an organized 802.11 network, elements of self-organization and intelligent edge become, I think, the way that you do that. If you do it right, you can get away from this problem, which is the so-called coverage first problem. Cellular systems tend to make their value proposition on the promise that you can get me anywhere, right? It's the can you hear me now thing, right? Now the difficulty here is, it means even if the cows in Kansas rarely use their phones, you probably have to cover it. And that makes for an expensive system. And if you do it with broadband, it means only a few people are paying to cover very large areas, right? On the other hand, 4G systems can operate a different way. Because of their edge intelligence, they can grow like an organism. So they can learn who their neighbors are. If a new neighbor gets added, they'll kind of shoulder aside and make room for the new one. If we do this right, that's one of the big challenges, in my view, of 4G systems. The self-aggregating, self-optimizing network, right? But they don't change in a vacuum. Devices change too. In cellular, the handset was the phone and vice versa, right? But as we moved into the 3G category, it became clear the device was more than just a phone. You know, maybe it's your browser, your data bank, other things. And wireless may be just a part of the bundle, right? And lastly, when you go to 3G, 4G, now voice may only become part of the bundle. And actually, this becomes a much more multi-purpose instrument. Will there be only one kind of multi-purpose instrument? I don't think so. I think we all like to choose the device that for us works best. But the point is, I think the devices, like laptops, will evolve to handle a whole bunch of applications. And we'll end up customizing them the way we want. Probably not the way a network provider was, like in the old days. And this says something else. The kind of multimedia that's going to be flowing is going to change a lot. In the old days, cellular systems grew from the isochronous model. They grew up to be systems that assumed everything was streaming bits. On the other hand, 802.11 grew up from the side that said, yeah, just a packet once in a while, probably okay. Well, these things are clearly growing together. And as we pass the millennium, we begin to get not just into the idea that it's one or two kinds of media, it's lots of kinds of media. And it moves all the way from asynchronous to isochronous, and it becomes a why can't we just all get along problem. And that becomes a MAC problem. The media access control layer is always really important. And you can see elements of this in the way first generation LANs moved into second ones, third ones, and finally into fourth generation systems. You can sort of see the things already getting added that makes this network cool, that says, wow, I want it. And I submit that most of the people I've talked to who visited AT&T labs and research, basically, they want this kind of stuff. Well, 802.11 is already working on 100 base T and higher. This will grow organically. Voice data and multimedia already starting to show up. A lot of these things are already there and growing. And I think we just have to add things in the right order to make it great. And one of the things that I think has to be added to make it work great is increasing the reuse dimensions, so that basically you can make a cellular-like network out of packet radio things like 802.11. And this is just one example of how you could do that. The time domain could be used to do different kinds of QoS. And you could use frequency and time to do some of the others. Just one of the solutions, not the only one. And also, you might also be able to make the system so smart with COG radio. Everybody know what COG radio is? The FCC's been talking a lot about it. It says, we'll give you the spectrum. Radio ports ought to listen a little bit and kind of stake their claims so they minimally hurt anybody else and make maximum use of spectrum. Well, one way this can happen is you literally let the radio ports sense each other's presence. And after collecting a bunch of data, kind of grind it up in a Cuisinart algorithm and choose the frequencies and or times that work the best. This self-organizing network idea is changing a lot of things, even the way spectrum is given by the FCC. The other thing that I know Larry pioneered and has continued to work on are the things that make radio better, make the links better, control the power budget in a narrower range. Things like MIMO, more creative use of different antenna images. All of those things are at the very leading edge of what radio is doing right now. And 802.11n, which is the higher rate task group, has incorporated space-time codes, MIMO, and beams, all at once into their draft standard. So it's very clear that you have to use these things carefully. You know, they don't always play well together. They can run with scissors. You have to control them, right? Space-time code is particularly cool because in the old days, you just sort of sent two wireless signals that were virtually the same. With space-time coding, as you probably already know, you actually send two different versions that are creatively different. And when you put them together, you get much better performance. So it's sort of like combining diversity and error correction coding. And it's really cool. So this says, if you're going to holistically design the next system, you might like to do like N has done. Because N was the first time in 802.11 that one of the task groups said, we're not going to just visit a single element, we're going to do two at once. We're going to co-design the PHY and the MAC together. And that gets back to this. It stems from an understanding that we are getting so close to Shannon as the physical layer now, that basically we can't afford to stretch it too much further. It says, where's the next element of the Pareto chart that we should work on to save that precious throughput that the PHY is giving us? And basically it's here, in the MAC. CSMA, the original 802 flavor, was great. It was inexpensive, simple, provided a good deal of reuse, if I can call it that. But the difficulty is, as the media becomes more challenging at streaming, it becomes harder and harder to simply use CSMA to hold the level of service constant. It says you want to go to a multimedia paradigm, a MAC that doesn't waste throughput and gives each kind of media the kind of treatment it really wants. So a small commercial, Larry knows this. At the labs, we invented a protocol called Mediaplex that basically is a kind of media control element that allows the radio resource to be used much more efficiently. It uses a combination of CSMA-like activities, but also reservations and a system of polling. And it also says, you got to tell me what you want. Then I'll give you what you want, if I've got enough of it to give. And basically it works like this. Those of you familiar with 802.11 already know what a superframe looks like. This system does a couple of important things. The first thing it does is separate access from bearer. Something well known to all cellular denizens like I am. But basically in 802.11 it didn't used to work that way. Everybody played on the same playground, whether you were seeking to enter the system or when you were already in it. If you use a separate access domain, it basically says you can use a point control mechanism to say, sorry, I know what you want. I've given out too much resource and I just can't afford to admit you at this time. But if you wait just a little bit, we'll try again. This sort of understanding of the radio resource gets you through or past the idea of selling someone the sleeves from your vest, which is essentially what CSMA does when carried to an extreme. Basically, its loading just increases as more people try to enter, to the point where it's using up all the throughput, just trying to fix the mistakes where people are killing the medium. So basically, this system, once you enter, uses a series of reservations triggered by polling, so that once I'm admitted, if I'm a stream, I actually get polled, and I take the information down from the network, and if I have information to send up, I do it. This is really good for stream-based behavior, and when coupled with a smart scheduler, it really works well. And in fact, we've documented how well it works. Regular 802.11, if you have a lot of clients and a lot of different streams, basically has trouble making it past about maybe 4.2, 4.5 megabits, even with long packets. But basically, a heads-up QoS MAC like Mediaplex basically gives you not only hard QoS, but also it gives you more throughput. With multiple clients and multiple stream types with different packet lengths, we can routinely make over 6 megabits. Well, if you get that kind of benefit in the PHY, you're very happy. So I think people have now stumbled to the idea that the MAC is the next place to look for more efficient throughput and to raise that throughput per user. And that's exactly what N is doing. And we actually put the core of Mediaplex into the new 802.11e QoS standard, which we started. And basically, it gives you a sort of spectrum of QoS options that allow you to go all the way from best effort is fine, up to, hey, this is really superb QoS, right? Carrier grade. So I'm not going to go through in detail. If you want, you can contact me or you can look at the e-spec and we can help you through that. But basically, I think the next thing that you want to look at is, well, QoS is only as good as interference lets it be. So basically, if you really want to make good QoS, you need a good MAC, yes, but you also have to have a channel worth having. And what that means is, you have to use the radio resource wisely, and you have to organize it in such a way that interference is held to a minimum. Not zero, but a minimum. And that goes with optimization and measurement. The first part is to understand what you have. And of course, Larry knows that, because he's made essentially his record on understanding propagation and interference, right? So basically what this invests an AP with is the ability to provide a standardized set of measurements that's available in what's called a MIB, a Management Information Block, so that the value that's in that MIB is always in the same place. Any system can look at it, and the measurement is always the same. It's not relative, and it's not proprietary to a particular design. So what this means is you now have one half of the way to make a really cool self-organized network. The other half is to be able to control it, not only with intelligence in a radio port, but even intelligence outside, if you want to. And that's what wireless network management is doing. And that study group which we started is really just catching fire right now. Started in January of this year, and now is moving toward getting an understanding of exactly what its scope is, right? So why is all this powerful? Well, for enterprise architectures, which is the way wireless LAN started, this is basically the way you put together a wireless LAN in a building. You probably have one of these here. So what it says is, if you add QoS with new radio ports and the new protocol, basically what it means is you can now do carrier-grade QoS for the voice over IP that you have here. So this is going to change everything, as they say, right? And voice over IP is definitely the new telephony, right? And it's being fueled currently by businesses who have had it with the duality of having to fund two very expensive communication systems. One of them was the old telephone PBX, which is notoriously expensive, but also, for most businesses, getting the end of its capital life. The other one is one that started out innocently enough as cheap Ethernet, but now has become such a staple of business that it now vies for IT budget. So what businesses are saying is, why can't we just collapse both of these into one? And so for businesses, voice over IP is basically a way of combining multimedia, customer relationship management, and all kinds of voice over IP and telephony traffic all into one system. So if you can do this wirelessly, this becomes what businesses really want. And the reason is, basically businesses aren't just, in the case of current technology, things where you sit at your desk and you have a voice telephone and a desk computer. It doesn't work that way. Basically, you don't know where you are because everybody's moving around the building. Everybody's doing business in real time. Remember that information half-life and the distance that you'll go? So you can't afford in business to have your business held up with key decision makers who can't be found, or inventory managers who can't tell you whether something's in stock. So basically all this is changing. And carrier-grade QoS, voice over IP, unified networks, and multimedia databases are going to change this like crazy. I'm going to skip over this really fast. Some of you know about TGI. This has been working on a kind of wireline equivalent privacy replacement called WEP. They got cracked a while ago. And so what they did was put together a sort of stopgap scheme that took elements of the standard and wove it into a fabric that is the so-called Wi-Fi protected access. And this is going to cycle back to pick up new things as it goes. So the solution now is just a phase one solution, and it'll keep going, right? And this tells you what I just said in words. You can get the talk from the leaf and read this yourself. And basically the problem is, as you might expect, 802.11 was an Ethernet cord. It was never meant for this kind of sophistication. So part of security is making the network integrous. And that's part of a common air interface. And it's something that 802.11 will have to assume to get to the point where it gets the dignity of 4G, right? And here's why. Security is really important because originally hackers just worked in a physical layer, right? Hopping, chipping, jumping, stuff like that, but they cracked it. Then next on the list was data link with MAC address verification. They cracked that. Then the network layer with web. Oops, cracked that one, right? Then the transport layer, right, which is IP authentication. But then we ended up with things like, identity spoofing. So now we're up to like the IPsec layer. And this is kind of stunning them a little bit, right? And secure shell web browser with the virus readers and applications like PGP, all of these are sort of the remaining citadels that people might use for protecting a 4G network, right? Now, why would you want to do that? Well, because 4G has the property that it bleeds into other applications. Just like all internet sorts of things, they become networks of networks. So, what are we going to do to join these environments? Will you have a bunch of disparate appliances, and will you wear them like a utility belt? Will you use expensive cellular calls just to speak to someone? If you have 4G coverage in your home, in your office, in your neighborhood. I don't think so, right? I think actually 802.11 has the capability with VPNs, virtual private networks, secure tunnels, for doing this sort of thing. And basically it says another thing. It says these systems can be fast enough that you might actually be willing to operate in a sort of multi-access environment where your device can do the best it can where it is with what it has, right? And what it means is the best of those connections may be so fast that literally you could pull down information and send it up faster than you could operate or create on it. And as a consequence, it spurred, and I suspect some of you do this, right? It spurred a sort of filling station mentality where you pick up your stuff fast, you operate on it, and then you move it back when you're in another 4G hot zone. So this is part of the organic paradigm. It's kind of like new to communications because we couldn't do this before. Communications was always kind of real time, right? So that means you effectively have to knit this together. And we at AT&T are changing our packet network, our backbone, our access network, and the transport to be able to do this, to literally cosmetically glue these various multidimensional solutions into as common a network as you can do. So that's a hot topic. Now, one of the places that you might want to do this is your home, right? Because right now, most homes are a sort of irritating patchwork of broadband and narrowband, mostly coming in over wires. And they're connecting a lot of electronic subnets in your home that you're putting in under the rug with staples or drilling holes in your home Swiss cheese, right? And even your car is in on this, right? Many people are talking about Wi-Fi in their car, right? In my view, you could have this. And wireless is something that can make this happen. And adding to the broadband wired connections in narrowband, you could actually have wireless. In my, some might say, hallucinogenic vision, right? Now, we actually tried some of this. And we tried it in a trial that we called WIN, Wireless IP Network Delivery. This was just a piece of that vision. It took cable, but it essentially put an entirely separate communication service on a channel that, with a relationship with the cable company, we were able to foster. And so effectively we had not a cable connection, but more like a pipe, a digital pipe, into the home. And then we put a wireless system with carrier-grade QoS and wireless voice-over IP phones, and even streaming video, and jukebox and everything into some sample homes. And the bottom line is, it taught us something. First of all, that had the oh wow factor. People loved it. Most of the people said, you will take this out of my house over my cold, dead body. Right? And the other thing they said is, this is my dream system. To be reclining out on the deck, watching the kids in the pool, doing my email, talking on the phone, and watching the Knicks in window on the screen. Right? And interestingly, we didn't tell them that. That's what people told us from the trial. They said, we now see where it's going. That is what we want. This is cool. Right? Now, what that says is, if you extend the vision, you kind of have a broken spot in the network linked to you folks. You have a PAN. A PAN is like Bluetooth or something like that. Maybe UWB to your plasma screen from the cable box, right? That's usually within a room or a couple of rooms. You may have a wireless LAN in your house, which is like multiple rooms and throughout your house, maybe into your front yard. And clearly, we have things like 3.5G and 3G cellular and WiMAX that are like sort of wireless DSL, but more likely like sort of slow multimedia for you. What I submit is, you have the possibility for making this picture complete. And there it is, the missing architectural element, the NAN, Neighborhood Area Network. Diameter about 1,000 feet. Right? The ability to reach to your house and then constitute a LAN inside your house. And from the LAN, a PAN, or whatever you want to do. Right? And maybe you could serve the NAN from 802.16 or fiber or millimeter wave system. Right? This can give you the kind of small cell performance, quality of service, and throughput that opens the pipe with the oh wow factor to you. And it's portable. You have it in your house, you have it in your neighborhood. This changes the way metropolitan areas can work, but particularly neighborhoods, right? It can actually supply a sort of community to a neighborhood again. And it can be part of what I call multi-tier networking. Why didn't anybody ever think of this before? Well, of course we did in the wired domain. This is how the Bell system made its money. But in wireless, we were always kind of encumbered by one thing. If you didn't use point-to-point communication, where the receiver can literally see the transmitter, you would be loath to use a diffuse system to then throw its throughput in such a way that it could be disaggregated to other systems. Because the quality and the throughput just wasn't that good. But now we've turned the corner. We could actually do that. So if you design a system that has transparent interfaces between those layers, has enough throughput, and most of all, is controllable and QoS rich enough to be able to handle multimedia, now you've got something. And now you can even mix and match. You could come in from Metro Fiber, go to 16, go to a PON, go to a wireless LAN in the house, or pick a different path in this pinball machine. But now you have a true mosaic. You can do what you want. It's like the internet, right? You can make it up as you go along. And it lasts the people who have in-home and in-building systems who are reaching up with devices saying, you'd really like to connect to a network. Now the networks can say, yeah, there you are. But the trouble is, Shannon, power, and basically making the right tool for the right job. And that's really what this chart reads between the lines. It says, don't try to pound a round peg into a square hole. Design the element of the system for the layer in which it best operates. Because if you don't, something in the multidimensional solution is going to fail. It'll be the rate. It'll be the QoS. It'll be the cost. I don't know. But clearly, if you had a system like this, now you can begin to think big things, right? here's the challenge that I'm going to leave with you. And I'm just about done, and I'm pretty much on time. Basically, the thing that kind of engages you about 4G systems is they're really cool, really fast, maybe as good as wired, work great with multiple and portable devices, give me almost everything I want. But am I willing to pay for them? If you look at a 3-kilometer cell, which might be the kind of thing you use for WiMAX or for 3G or something, right? You basically divide that throughput among lots of people. And consequently, you tend to get sometimes disappointing throughput if you have a lot of customers, right? With small cell 4G systems, you could fix that. But look how many cells you might need to cover the same area. With some overlap, you might need 125 of them. This means you have to make the network and the APs and all of the infrastructure that operates it so cheap that you could offer service that was comparable to what people wanted at a price that was about what they were paying today for lower throughput and poorer service. So in my view, although I am a technologist, and I love to work in radios and networks and all the rest, that's a big problem. This is where we need good research minds, because this will end up being a holistic solution. What we will need is the best of radio, the best of MAX, the best of network and network management, and radio resource management, and the people who put networks together with real stuff and make them into money-making and user-satisfying systems. That's where we'll need the holistic approach, and that's where we could all use a lot of help. So I hope you, as the future researchers who will help us do that, are up for the task. I am. That's my mission now. So I hope you might join me. So if you want to learn more about neighborhood area networks or join the community interest group or whatever, you let me know. Lalitha can put you in touch. And if any of you have any questions or comments or whatever, my email address is rrm, Radio Resource Management, at att.com. Okay? Thanks very much. It's been a pleasure speaking with you today. Really enjoyed it. We have about 2 minutes. Any questions now? Or have I so thoroughly frightened you or bored you that you... That's what I hoped. Okay.
I don't know. I do have a question.
Oh, I knew you would.
So the issue with current 802 and VPNs is that there is no handoff system of the existing 802.11 networks, and hence VPN is simply not feasible if you wanted mobility with a VPN.
I'm not going to bore you by running through all these slides backwards, but TGR, which just started, is working that very issue. And I personally like IPsec, right, because it allows you to encrypt the entire connection across that multi-tier network so that you effectively encrypt everybody from user to user, not just a little piece of the network. So actually part of what I've been working on with others at AT&T is to see if that vision actually works. And we've actually engaged with some semiconductor partners to try to put IPsec engines on the Wi-Fi chips so that basically you can put together a complete integrous connection like that. Right? But that's just one solution, and R is working other ones. And R seeks to make QoS and security persistent across handoffs. That's its mission. And Bill Marshall, you might remember from, he's a researcher, he's there a long time, helped develop DOCSIS and was active in voice over IP spectrology for SIP. Basically, he's the editor of R. So we're working hard on that. So if any of you want to help with that, get in touch. Thanks for that question.
Where's the MediaPlex going? Is that going to be standardized as part of this?
Several vendors are implementing the full AT&T version of MediaPlex, and we'll be using that. We will be able to drop back to what's in 802.11e, which is called Hybrid Contention Controlled Access, HCCA. it contains the core part of Mediaplex that is the T-spec, that is, I ask for this resource, that's called presenting your T-spec, polling, and the reservations that allow that streaming stuff to get through with a reservation-based guarantee. So we're supporting that, as well as EDCA, which is the statistical QoS, because for some systems, like small home systems, you may not actually need the full-blown reservation-based system. So HCCA may not be necessary, and EDCA may be fine. But I predict that as we move forward, more and more of you will change out your DCF stuff. Because in the end, we are multimedia animals, and I think we're going to want multimedia. And if you load heavily these DCF systems, you begin to see the trouble with them. Basically, they begin to act up. And it'll appear to you first as, it's funny, when I make a voice over IP phone call, and when I'm looking at the plasma screen with a movie, the plasma screen makes mistakes and the voice sounds bad. Right? So you may not immediately make the mental leap, well, this is a failure of the Mac. Right? But it really is. Right? So people will learn these two modes are now mandatory in 802.11e. Vendors are stepping up to building them, and Wi-Fi will certify these modes. The Mediaplex mode, which separates access and bearer, is actually more useful for neighborhood area networks than it is for the final LAN delivery. And we're pursuing that separately with other manufacturers, with, shall we say, the community of interest manufacturers. Yes, sir.
Do you think that there is a big problem that prevents voice over IP being deployed in
Oh gosh, no, there are lots of problems. QoS is just one. I think radio resource management is another, right? Because as I said, the Mac could be as good as you could make it, but if you had too much interference, and the interference was uncontrolled and definitely troublesome, then what good is a good Mac? It's crap, right? And again, there are other elements. Security. You're going to want security, right? Because voice over IP, we do lots of talking about things we probably wouldn't want others to hear. And that was an embarrassment to early cellular. I remember when Prince Charles had a little incident where they intercepted his cell phone, right? So, I'm sure he switched to a secure channel immediately, but then it was too late. All of us would like, with the persistence of hacking, to know that our communications were safe. And I think that'll extend to voice over IP as well. So there are many elements, and that's my principal disappointment with 11. It's at once my biggest joy and my biggest disappointment, right? The joy is we have exquisite networks of experts who are working on those things. And it allows us to make headway really fast with the best in the business. And we get the coupling direct to vendors and chip makers. So there's no horrible delay. Like, will you make this chip, please, please, please? Everybody convinces themselves they're making this chip when they're making the standard for it in 11. That's the good part. The bad part is it's not being designed entirely holistically yet. So sometimes the connectors don't fit, right? And you got to go back and you say, well, when I plug you in, you spark. We got to go back and find out why and fix that, right? So 802.11 is dealing with that. But to his courage and I think persistence, I congratulate the chair of 802.11, Stuart Carey, because he has at last embraced the challenge to make 802 holistic and multi-layer in the stack compliant. Right? He said, no, we're not just an Ethernet cord anymore. I challenge you folks. He said this to 1,000 people in a big meeting at the end of last year. He said, I challenge you people. Think out of the layer, right? Don't be afraid to be social climbers. Go as high as you have to make this a good common area interface. So he's leading in the right direction, and I think the boat's turning. But it's a big boat. It's got 500 people, so it'll take a while. Yes, sir.
One question that point a bit further. If you look at previous experience, say in IETF, they needed mobility, multicasting, and other features like QoS. And the standards came out, there were lots of working groups, so it didn't get implemented. And the lowest common denominator, which was just the core packet switching, was the only thing that survived.
Right.
Why won't that happen with 802.11 all over again?
It could. And I've told Stuart Carey that the challenge is ours to lose.
But is there even an intellectual path which takes you to a success point? Because I see that 802.11's biggest strength is its simplicity. You just plug it in, it's relatively neutral to upper layer protocols. The moment you start adding lots of features with APIs for QoS and security, who's going to want to put
No, I think you've perfectly teed it up. And I've talked to the chair of TIA, Anil Kripalani, you know, Anil, I think, right? And he and I are in the same space. He's dealing with a 3G that's scrambling hard to try to make itself right. And he knows 802.11 is scrambling hard to try to make itself right. And we've both cried on each other's shoulders saying, wouldn't it be great if we could make a sort of collaborative effort and both make it great? But look, I think this is a race. There are so many bright people who are doing wireless now, and there are so many possible solutions that basically it's not just a one-size-fits-all anymore. So somebody is going to get the right combination of stuff together, and they're going to do it. I think 802.11 has a good head start, and I think if it changes the way it operates, if it adds the right things, and if it keeps its eye on the prize, I think it can make it. But I'm partial. And I've invested a lot of time in 11.
I invested time in the 90s on this stuff, and I came to realize, not something I believed then, but the simplest protocols which can easily be stacked and work together are the ones that survive.
Right.
Anything that leads to a vertical stovepipe is very risky and may not be.
Exactly. And that's why there's a mantra in 802.11 right now that can get you instantly to the head of the ballot resolution comment line, which is, this is too complex. We're going to make this simpler.
Right. But there's also another theory that any standard commit with more than 50 people is doomed to failure, and there's a certain point where 50 becomes 500, and IETF actually has peaked out at 2,000, and none of those standards.
I have just one word for the professor, microdots. Seriously, I think 802.11 is trying to do that too, because every so often, 11 does what's called a maintenance activity, where it takes the various separate task group substandards and pushes them into the main standard. So after a while, all of these new ones will get subsumed into the new ones.
I think that's
And maintenance also has the charter to make it simpler, at least in the essence of explaining it. Because one of the criticisms of 11 is, wow, everything is everywhere, right? So the implementers have difficulty, and as it gets more elements, then the interchanges become more complex.
the holistic approach and keeping it simple and then scaling down frequently might help.
Come to 802.11. You and I will pound on Stuart Carey together.
I'm not going to.
He's a good guy. That was a great question. That's exactly, I think, the problem, outside of the cost.
If I knew a solution to this problem, I would go, but I don't know.
Okay, we can talk anytime. Are there any other questions? No? Yes? Okay.
Why do you think an operator will operate a 4G network? Why not the current model where everybody installs latest and greatest base station and this operator is hooked?
Actually, it's a good question. And I left one slide because I knew I would get this one. So thank you very much. The check is in the mail. Here's the last slide. Basically, I think it's going to change the paradigm of how service providers, the government, and users, and most important, municipalities, work together. I think networks are no longer a single company or even a couple of companies producing the network for you. I think that's like long ago. It's too expensive to make a network now. You cannot afford to make big mistakes like this as many companies have learned the hard way. And even if you could, you wouldn't be able to get the regulatory spectrum and other things to align. So I think it really is a team effort. I think users are making the choice every day when they buy a device. And I think service providers are saying, you know, my money is delivering services, which is like multimedia, things that will pay for themselves, to people. How do I get there? Right? There's a dotted line now. Really hard to communicate over a dotted line. Can I afford to put in this dotted line? No. Spend a lot of money on the core network, a lot of money on the transport network, a lot of money on the edge network that gets you to the access, but I still got a dotted line. What do I do here? I think a fertile area is metropolitan areas. And I think the metropolitan areas think so too. And I think I'm going over time a little bit here, but basically, I think people in Congress admit our telecommunications policy is making us a second-class country. That's number one. Number two, cable and DSL are not enough choice. And number three, the FCC is basically not making enough raw material available, so other solutions arise. And so, faced with those challenges, I think metropolitan areas are saying, I'm not sure I want more DSL or more cable. How about if I supply the connectivity? I supply water now. I may supply electricity. A lot of municipalities supply their own electricity plant. Why can't I supply communications? And Congress, the FCC, and other people are listening. And they're listening to people like this group. And there are many cases where fiber, for instance, is going municipal. And I see no reason why spectrum can't go municipal too. And this is a theme that's catching root in Washington. So I think it's going to be a team effort. I think it'll be service providers. I think it will be other transport companies. I think it will be users. And I think it will be municipalities that make this whole thing work. Nobody's got enough money, time, or smarts to do it all themselves. Just my view. But thanks for teeing up that last slide. That was perfect. And I do not know this chap, but I'd like to. Okay, any other questions? Okay, looks like not. I really enjoyed it. It's been great.